So thus far in the first 4 lectures, we have seen collection of data through different API calls. We have looked at HTTP requests. We then looked at validation of data, which was Pydantic schemas. We looked at JSON-based cleaning. We then looked at labeling the data set, and we looked at different kinds of labeling tasks. We looked at tools such as Label Studio. After that, we realized that the labeling can be optimized. We cannot technically label 20,000, 40,000 samples as a single person. So therefore, we need to optimize it, where we looked at techniques such as active learning. The main premise was that not all samples are equal. Some samples will offer more advantage to the models. Can we have the laptops off, please? So let's say that after collecting data, validating, cleaning, labeling some initial data, optimizing the labeling with active learning, we have still perhaps reached 80–85% accuracy. We still want to increase the accuracy even more. The kinds of models that we are using is neural network deep learning kind of models, which generally show better performance with larger data. But you do not have more budget for labeling more samples. You still have a lot of samples. What do you now do? What could you now do so as to somehow increase the number of samples so that your label data set becomes larger and your deep learning pipelines can be more accurate? Okay. So today we'll be looking at how we can augment the data set, which would mean that we know the exact transform we'll apply to the data set and we know the label. So this will help us increase the data set size without having to spend more effort in collecting the data. So let's take one example. We can start off with an image of a cat. We know this is a cat. You can flip it horizontally, you can rotate the image, you can change the brightness, change the color, zoom in. The zoomed in version seems like a very passport size photo of a cat. You can add some noise, change the contrast, slightly crop. You can do all of those. Importantly, in all of these images, if it were a binary classification task, would you call this image as a cat? Yes, there is no change in that. So we will have to maintain that the labels are preserved under this transformation. That is what we want. You've seen a few examples. Now think of this. If you were to apply this kind of transformation to your data set, now you have 8x the data set size. Do you need to collect more labels? No. So the reason why we do this is the technical term behind this is invariance. Our vision, which is the human vision, as well as what we want to enable in neural networks, is that they're invariant to slight transformations. So this is also to say that this is typically how we can get some more representative data sets out of some smaller data sets. We can try to simulate the different scenarios in which perhaps a photograph would have been taken. And we know that if we see a cat as a cat, whether you translate, you rotate, you flip, you will still be able to see it as a cat. So we want to enable such properties in neural networks. This can be done by design also. We can have certain neural network variants which will have certain kinds of invariances to shift as well as rotation. So those are like convolutional neural networks enable such some of these properties, but more generally we want to get the invariance problem solved. We want the neural networks or the models to learn this invariance. And it is not that we are not used to it. So those of you who use filters on your on different apps, you are already using data augmentation. Now whether a scene is shown as the base, the original image, or you are modifying it to look slightly better, you are just augmenting, you're presenting the same views, different views of the same data. So it's something which we're very used to, just that we don't know the technical term for it. So in fact, I don't know how many of you follow different YouTube channels, which if you go in detail, you'll also realize that the photos which are taken from your phones are largely software photos now. So it's primarily now called computational photography. What you finally see is perhaps not the same as the raw sensor image being taken. There are a bunch of these computational filters being applied. So I want this class to be more interactive, given that this is a very practical topic and we can just think through this. Thus far, these were images. If we think about digits, why do you think augmentation might help? Like we're seeing some 7 being written. Why would augmentation help?
Because say if you are making an OCR model, so the scans of the users using your OCR model would be inputting images of differing qualities. So it could be a blurred image, it could be with noise, it could be dark, it could be light. So you have to augment more accordingly.
Okay, good. So you are talking about the input quality. And by the way, this is not a very far-fetched problem. So this is something I have also been talking to a few colleagues and been contemplating. So could we just scan all of your answer sheets which you give for exams and then have them automatically checked once we have developed LLM-based solutions? No earphones, please. So that is one. The input quality will itself vary depending on the lighting conditions you have taken the photo, depending on the angle, the orientation, all of those. What else makes it useful or what else prompts you to think about augmentation? Can you remove your back, please? Yeah. Right. What else makes augmentation useful? How many of you have horrible handwritings? Not worse than mine. So if the system can detect mine, it can perhaps detect most of yours. Different people will write 7 differently. We're seeing this canonical 7, but then also some people put a line in between. Right? So people write 7 differently. People have they'll use different pen, they'll use different kinds of thickness. Some people write very thin, some people write very fat. Some people write with a lot of indentation. So they may have some inclination, they may have certain negative inclination, positive inclination. So you can see that there is a lot of variation which will exist in some real world data. Unfortunately, which will not be present in the data sets which you may get publicly. So therefore, if you have to enable any real application, you have to think about the different scenarios in which these could be taken, the input could be taken, as well as the different kinds of input coming from different individuals. So subject differences due to subjects, different due to the input conditions, difference due to a lot of other things. Similarly, the biometrics, like you're currently marking your attendance on the biometric. You have to have the system be capable to work with, let's say, 1/4 of your thumb, with a full thumb, with a slightly rotated thumb, with an injured thumb. The facial biometric, you want it to work in very poor lighting condition, in good lighting condition, in sunlight, in the night, in the evening, with slight rotation, with spectacles, without spectacles, right? So think of all the scenarios in which you have perhaps seen any of such biometric machine. Even if you go for Digi-Yatra like systems, they have to be fairly robust. Now, so it's one thing to increase the dataset size, but do you think it brings in utility? What could be some benefit of increasing the dataset size through augmentation? Sorry?
We cater to subjectivity as well.
Yes, you can handle a lot of subjectivity, a lot of variances. In terms of some objective criteria, can you tell me? Eventually, when you look at any machine learning model, what is your main goal? To have good accuracy of performance and good generalization. So it will offer both these things. So if you look at this survey, this is a slightly old survey, pre-COVID survey. If we look at a baseline model, this was giving an error of about 7% on some data set. If we do some simple augmentations, which is you're increasing the data set size by let's say 2-3%, 2x by applying some flips, by applying some crops. The error rate goes down, the improvement is about 2%. Cutout, which we'll see today, and there are multiple other such augmentations. So the important thing was that augmentation works. It is not just some random abstract idea that we are presenting. There are papers which have shown, and there is an active area of research which figures out what can be better augmentations to increase the accuracy without having to increase the dataset size. In fact, one such niche area, not exactly niche, one such subset of this area is known as where you have synthetic data, completely synthetic data. Why do you think synthetic data might be useful? Yeah. Okay, good. So you can create some synthetic data which corresponds to some of the statistics being matching, as well as you can still ensure that the privacy is maintained. What might be some other reasons for this?
You can generate a really large data set.
Good. We can have, you can have much more larger data sets. Good. Any other? Yes.
We can cover any exceptions like if we think in our mind that can be possible.
Good. So let's say that you have, the images that you have are in your data set are all perhaps of the Western context, right? You're somehow using an image, you're trying to classify maybe the age of the person. Now you don't have any images of the Eastern context, let's say India or China. Now if you give such a system, will it work well? Probably not. Could you then create some synthetic data where you know the methods, you can swap out the faces, put in the Indian faces, put in the Chinese faces, and perhaps get the data from there, like get some label data also. Can you increase the dataset size significantly? Also think of certain other weird cases. So let's say if you want, so let's say some of the systems, some of the places where the system is making mistakes are very novel cases. Let's say horse on water. Typically you may not have a lot of images of horse on water. You may have horse on grass, horse on dust, whatever. If you can create such synthetic data sets, like I believe all of you are using ChatGPT like systems or Nano Banana or such kind of image generation, DALI like image generation tool. So if you can create such data sets, your overall data set becomes more diverse. You can also then ensure that there is lesser errors on less represented classes. Okay, now why does augmentation work? This is a very simplistic view. Perhaps if we were trying to just find some pattern in this data, the left hand side one is showing you the data points without any augmentation. And if we try to fit any pattern to this data, we will see that we can end up with a very, very sophisticated pattern. This surface that we are seeing, which is very sophisticated, this often leads to behavior which is borderline memorization. So it's trying to learn the specifics, the intricacies of the data set as opposed to learning something more generic. But if you were to increase the data set size through augmentation, you will often end up seeing that we may end up learning a more generalized boundary, which seems simpler, but more generalized, lesser memorization. So this is one way in which the augmentation literature is generally motivated, that it can lead to more generalization when you have fed in more varied samples with the correct labels. Okay. So in the remainder of the lecture, we will now go through some different kinds of augmentations. Again, many of them will seem very intuitive. So keep attempting answers. You will see that the lecture is not very difficult compared to perhaps the previous one, which required a slightly deeper understanding of acquisition functions, maximization, minimizations. Today will be slightly simpler that way. Let's look at some transforms. The original image you can do in horizontal flip. Is it still a dog? Yes. You can rotate the image. So if we rotate the image, do we need to do anything for these white patches? What should we do? Sorry, one at a time. No, I meant this white triangle which is appearing, which was not previously there. It's coming because you've rotated. What do you do with that? Do you present it as it is?
You could do two of them, right? You could find the largest rectangle that fits in the rotated image.
Okay.
And you could also present it as this.
Okay, you could do some sophisticated transform to somehow fill this, but will that be correct or not is another question. What else could you do?
Could find it with
Sorry. You can mask, okay. So your model has to have the capability of having masked inputs. You're saying something?
You could find it with zeros.
Yeah, which is the other way of masking. Sometimes this is done in combination with another filter which is just cropping. So then you again zoom into it so that the overall size remains the same, and then you still are able to not having to cut these boundaries. Or how many of you use Photoshop? Could you use something like generative fill in Photoshop? That would just fill out this area with more sky, with more grass, with the legs of the dog, etc. So you could do those things also. So it's really up to your creativity. We could scale down, we could translate, which means move, we could crop, we could take a crop, or we could also do a scale up. So crop and scale up, you can see, can be comparable depending on how you use them. Importantly, if this is a classification task, the labels will remain the same. If this were a segmentation task and or multi-class, multi-label problem where you have to give multiple labels. Like for the first one, we'll give the label dog, sky, grass. For the last one, can we give the same labels? No. So therefore, you have to be very sure about what the transformation is doing, and for different tasks, we have to see whether the labels can automatically be copied or not. There are some other simple kinds of transforms. You can increase the brightness. So what do you think brightness and contrast what kind of generalization capabilities would this give? Increasing? Right. No. So my question is, so for these we are saying that perhaps if the photo was taken from the other side or the photo was zoomed in further, then also we would expect the system to work well. For the color intensity transforms, what is the equivalent statement? The lighting conditions could have been different. The filters, the camera, the ISO, all of those could have been slightly different. Okay, this one is interesting, slightly non-trivial compared to the earlier ones. So if we want to do some transformation in handwriting, we can do the ones which we have been discussing. We can also perhaps make the stroke a little thinner or slightly thicker. But one of the interesting ones is to put this random distortions. So these pixels, these grid points, we can just randomly move them in the space as per some directions, and then eventually you will end up with a result which looks like the following. This will simulate the different ways in which people can write such text. And you can again potentially do infinite of these. So that way you'll get a lot of different styluses. Self-driving cars. So when we think of self-driving cars, unfortunately some of the accidents in the past have happened because of scenarios which are not represented before, like a tall building casting a shadow in front of the self-driving car has previously confused those. So therefore, can we augment them with some different weather conditions? You can put rain, fog, snow. Now how do you do this? How do you augment the different weather conditions?
Maybe give a picture of the data set, like of real condition to the model.
You have to give the real condition. Perhaps let's say the real condition is clear. You have to give that, and then what else?
Maybe we can overlay it with. You could use generative models like you use in this.
You could use generative models. Okay.
Can we give parameters like temperature
Okay, good. So we are looking at different views of this. I want more answers. This is a very interesting kind of an application. Think more. We have had thus far two different answers. Both of them are two different paradigms. One is saying just use generative fills and just give another set of images of those conditions, some images of fog condition. Another student is saying that perhaps also give the physical parameterization such as the temperature, the humidity, etc.
You can only really give temperature, humidity, etc. if your car has those sensors in it, right?
Just imagine we have those. Yes. 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 So the reason I mentioned there are two different paradigms is, one, you could completely work at a pixel level, just as how images are being generative. Second, you could work at a level of physics. You know all the physical conditions. If you knew perfectly the temperature, the humidity, 180 different parameters, whatever number of parameters, could you figure out how that would look like? So if you can build a physical simulator, and then how the physical simulator leads to images. If you've learned that, so think of, right, so let's think of this example. How many of you played games like GTA or some of the other games? So are the conditions realistic? Right? So they have to have some kind of a simulator, which apart from kicking someone out of their car, so they have to have some kind of a physics engine which can simulate the conditions quite well. Although they just show very clear skies, etc. We should have a GTA Indian environment also, and then we'll see how good that performs. So we have to have some kind of a physics renderer, and then that creates an image. That would, if that works well, that would be better in practice as opposed to just working at the pixel level without having any knowledge of the physics. Because you can then end up with something which is physically inconsistent. In higher temperature, lower temperature, the fog condition might be varying, which could be untrue. Any questions till now?
So maybe the car could be itself taken for like while making it and improving it could be itself taken in that condition to test.
Okay. You could take the car in that condition, but if perhaps you have to do that in India, perhaps, let's say, you would have to take the car from Kanyakumari to Kashmir to, and then Dwarka to Guwahati or somewhere even eastwards to capture all the diversity. It becomes it becomes very hard. Therefore, for a lot of such problems, this is equivalent to why don't you let pilots learn on the real planes? You could, but it's not a very good condition. You have to make them learn on simulators. So therefore, these simulators have to be very powerful. They have to be able to mimic those situations. And then finally, the modality that is coming out of the simulator is an image, is a video. Right? So all of that physics has to be embedded to create a final image. Yes.
Can you go back to that slide of geometric transformation? Geometric transformation.
Geometric.
So there seems to be a trade-off between how much variability we can introduce, because if we introduce much variability, like if you translate a lot, then we will lose labels, right?
Good. So therefore you cannot be doing this madly. There is a system, there is an art and a science to it. You have to learn both to understand that how much is feasible.
Can we do it mathematically? Because manually, like learning that how much we should do it, there should be some hyperparameter that can control it.
There is always a hyperparameter which controls this. I'll come to this in about 20 minutes. We'll come now. Other questions?
If we are doing augmentation to prevent overfitting, if we don't augment enough, isn't it going to lead to even more overfitting?
I didn't get that question. So the question is, let me paraphrase and try and understand. We are using augmentation to reduce overfitting. If we don't augment enough, then won't it lead to more overfitting?
It's basically more of the same samples or very similar samples. If we don't augment it enough. So won't it lead to the model just memorizing more of the same samples?
Yeah, so therefore so that is the art part to this also. You have to, so that is why you cannot just randomly just augment and expect an improvement. Therefore, this is also, a lot of it is also empirically figured out. And you have to also introduce enough of these nuances to be able to then see the effects. Like translation, so think of translation as giving the model the capability to predict irrespective of where something is in an image. Now that additional capability will only come when you are providing such samples, right? So you're giving the model more such, I would say more such levers which it can capitalize on. But it is still not very trivial. You still have to do a lot of experiments to figure out the right balance. Other questions? Okay. This is where things get interesting. Thus far we have been saying flip, change. But if you change B, if you apply a transformation to B and you're careless, you say that the labels don't change. You don't. So therefore we have to be careful whenever we think about such kinds of augmentations. By the way, I don't think many of you will remember, but as kids, these are the most confusing characters. We end up writing them the wrong way and it takes about 5-6 years to figure out the correct ones. Similarly, 6 and 9, and similarly the image of the X-ray. So the X-ray image looks quite innocent, like you can perhaps just flip it, but sometimes in certain medical conditions, this is a curated example, this might not be perfect. Let's say if shows the position of the heart has changed and if you give it to a doctor and the doctor may say that you need to be immediately shifted to the operation theatre because your heart is displaced, something like that. So therefore it's not always recommended to change things. You still have to figure out, you have to do this carefully. Other kinds of augmentation include adding noise. So the noise can be in terms of some Gaussian noise being added, which is to some subset of the pixels, you just add some value which is perhaps normally distributed with mean 0 variance 1 or mean 0 variance something. You can put salt and pepper, which is some white, some black pixels. You can put some speckled noise. So therefore, there are these different kinds of augmentation you could do. For OCR, now you want to be able to, you also want to be able to get it working for the cases when when the lens of the camera was not clean, or whether you ended up for some reason taking a blurred photo. So therefore, you can add some element of blur to your photo and you still want it to work well. But don't go beyond a limit where it becomes incomprehensible. Okay, now we get to more interesting kinds of augmentations. This particular augmentation is called cutout. So you remove some pixels, a patch of pixel from an image completely. Just remove it. So just make it all zeros, make it all ones, some sentinel value you put. So you can pick up from the head, from the tail, from the feet, from the abdomen, you can remove those. Why do you think this might work? Good. It can reduce the dependency on only some small subset of the region where the model could have been focusing on. I had given an example of this earlier. This was during COVID. A lot of researchers were working on models which could predict COVID from X-ray images or something like some input modality like that. And one particular system paper showed very good accuracy, close to 100%, but it was focusing on the name of the lab. So if instead of that, if we had given it enough augmented images, and in some of those, that was weird. So in some of them, if we remove the name of the lab itself, then does it still work or not? And then still it has to tell whether it is COVID or not. Perhaps it will work out with this specific kind of an augmentation. So these kind of ideas occur in different kinds of places. How many of you have implemented neural networks? Written neural networks? Okay. Not everyone. So you have something known as dropout neural networks, where you drop out some of the nodes. Here you're dropping off some of the inputs. So you'll see similar ideas repeating. So this was cut out, and all weird kinds of ideas now you'll see. You have a dog image and you have a cat image. You combine them 70-30. Right? And then you will get this ghostly blend of an image. Now, what is the label of this image? No, so for labels of such images, I'll just write this on the whiteboard. Let's say that for the first image, let's say we're working only with two classes, cats and dogs. So my labeling is of this form: is dog question mark, is cat question mark, and we'd expect only one of them to be a 1. Right? For the first image, we have 1, 0. For the second image, we have 0, 1. For the blended image, it's 0.7, 0.3. Right? So we're giving this 2-length vector, and the label for this, for the first image was 1, 0, second was, rightmost image was 0, 1, and for the blended image, it is 0.7, 0.3. Right? So you're able to create such non-existent concepts in the image through this mix-up. And in the literature, it's shown that it can help with smooth the decision boundaries between the two classes. The ideas will keep getting weird now. You take an image of a dog on the left, you take the image of a cat, and you cut the head of the cat, you put it on the body of the dog. This is called cut mix. Now the label in this is the proportion to the area, in proportion to the area. This might not be perfect because maybe the face is more important in telling the species. So in this case it will be 0.75 dog plus 0.25 cat, but I sense this might be a very difficult example now, because the cat, like if the Photoshop was done slightly better, you could actually think of this as a cat, because the dog body is not sufficiently given. Yes? How does this help? I think it is just adding some.
Maybe if we still label it as a cat, then it helps because we focus on the very features we want to bifurcate on, not on the background.
That's a good point. In this case, according to what we see on the slides, because 75% of the image is still dog and 25% of the image is a cat, we'll end up labeling it to be a dog, which would be wrong. But the intuition is correct. If we can somehow show similar to this intuition, that we are figuring out, we're not having the dependence only on certain parts of an image, we're making it more general.
So like if we zoomed it out a bit, so that the more surrounding was visible and the dog area was less, and we switched the dog to a cat, but the surrounding of the dog remained, and in that case the area of dog became more, so the label would become incorrect that case, if we were judging by the fact of age.
That was a lot of things you said,
So means
but I think you're correct. No, so I think in some of these cases we have to be little careful, and we have to take a slightly nuanced approach about what the final label is. This illustrative example might be a bit misleading in that case. Yeah, I'll try and figure out if we can get some better examples, maybe from the cut mix paper itself, where they have shown such motivations. Let's see if we can do this live. So this is the image that they have shown. Typically the first paper is the first figure is what we want to look at in such papers to see. Yeah, this is 60% dog, 40% cat. But I think in this particular image, it seems to be a close crop of the object of concern. So in that case, I think it is still feasible. But in cases where the background will be significantly dominating, I think this might not work that very well. If the crop is not tied to the image. Yes. If you had to manually label, then it defeats the purpose. It defeats it in some sense. But yes, that is correct. Now, different tasks will involve different kinds of augmentation. For classification, we have said that we can apply these rotate, transforms, shift transforms, etc. But not for all. B and D, remember the B and D example or the X-ray example. For object detection, will we also have to change the label? Because the object will now also have shifted. We'll see this in more detail. Segmentation, pose estimation, each of them will require a slightly different and nuanced approach towards creating the labels for the augmented data. Like this case showing for object detection, let's say that the original box was 50, 30, 200, 180. Now the starting position itself has changed. So it's gone to 100 and then 30 to 50, 180. So it will end up creating a different box now. So therefore, when you do the change, when you create the augmented view, you will also have to change the label in this case, the bounding box in this case. With respect to segmentation, if we were to, let's say, rotate the image, we'd also have to rotate the segmented mask. In some cases, the segmented mask may also have to get cropped. It may not be fully present in the image. So I have given some sample code which we can use in the labs. So it's using a particular library called Augmentations, which provides very trivial functional, very trivial amount of code is needed to create such kind of transforms. So in this case, we were transforming with the horizontal flip, rotating, and some brightness contrast. And then we said that there were B box, which is a bounding box params. And then once we apply the augmentation, we'll also end up changing the bounding box. Automatically, it will help happen through the library. Similarly, we can do for the segmentation also. Okay, now let's look at some different kinds of tasks. Named entity recognition, we've been seeing this task a lot. If the original was John Smith works at Google in New York, we may want to change it to something like John Smith is employed at Google in New York. This is the way you would typically change the variables in your code 5 minutes before the deadline when you have borrowed the code from your friend, so that it doesn't get flagged by the TA in plagiarism, something like that. Could we have changed John Smith to Frown Smith or something else? No. So therefore, the entity token should not be modified. It's the other thing which can be changed. Could you change works at to worked at?
No, changes the context.
Worked at means they used to work at Google, works at they're currently working. So you have to be careful with what all you can change. Typically just using some kinds of synonyms is fine. Again, there will be some good libraries which we can use to apply such kinds of transforms.
So, highlight why we should not change the stats.
Right. Oh, I see. Okay. So his question is, why should we not change it? In one sense, if we're just increasing the dataset size, yes, you can just change instead of John Smith, Doe Smith works at Microsoft in Manhattan. You can do that. Yes. So if it were, so the context in which I was said was that let's say if you want to, for a very specific kind of an example, you don't want the answer to be the same. If you want the answer to remain the same, in that case you won't want to change. Depends on the specific task at hand. I mean, if you wanted to extract John Smith, Google and New York only, then you won't change. Otherwise, you can just template these out and then just instantiate the template with different variables.
You can also replace it by work set, no?
By?
By work set.
Yeah, so again, it depends on what your specific task is. Let's say if given the sentence, the question was, who all are currently working at Google? Then your answer will become wrong. Right? So accordingly, you'll have to change the label also. Then you'll have to say that currently working and used to work. Right? So it depends on the task. In this specific example, if you want to retain the overall entities, then just applying some synonyms to the words should be sufficient. Phrases should be sufficient. Pose estimation, if we do a horizontal flip, we'll have to move the right to the left and the left to the right. So this might seem like something trivial, but I don't know how many of you have seen this, that you have to factor such things. So at least your Zoom app gives you this option. Have you seen in the Zoom app, you can flip the video, whether you want it to be natural, whether you want to get a flipped version. And this happens to me sometimes when I'm changing the camera. I move in this direction and I actually have to move in this direction to come closer. So you have to figure out that, and the key point augmentation, according to the direction, according to the flip, you'll also have to rotate those points accordingly. So OCR we have already looked at. So generally when we want to think about such augmentation pipelines, we end up, this was one of the questions that Mayank was probably asking, that if we have an image, we can have this suite of these transforms, flip, rotate, brightness, noise, and each of them we perform with a given probability P. Flip with a probability P equal to 1.5, rotate with a probability P equal to 0.5, brightness change probability P 0.3, noise add probability P 0.2, something like that. So you can then have simulate these through different values of P. So if you just toss the coin multiple times, you'll end up creating various different images for this. And if the task is safe, which means you don't really have to worry about changing the label, it means you can get various augmented views without having to do anything sophisticated. Questions? Okay. This we have already seen. So generally, if we think about different domains, with natural images, we could flip, rotate, color jitter. Of course, you don't want to be flipping to the extent that it stops obeying the rules of physics. You don't want to have a human being standing upside down. Medical imaging, more or less with only some mild rotation of brightness, you can do. Flips, you don't want to be doing. You don't want to be moving your heart to the other corner. Satellite imagery, you can typically do any kind of rotation, any kind of color shift. Documents, you can do some kind of rotation but not huge, otherwise it will become undecipherable. And for digits, you are again okay with rotation but not significant rotation. Let's look at some more text augmentation examples. Now this is for sentiment prediction. So the question is, the original sentence was the movie was fantastic. Now you have to use your creativity. The film, you change the movie to film, which is a synonym. You can change this fantastic to wonderful. You can add some filler words. The movie was really fantastic. And then you can delete some, which is also mimicking sometimes how human beings would write. They might miss out on some things. So all of these would be okay augmentations. Can someone tell me some wrong augmentations for this example?
We cannot take fantastic.
Maybe the movie is deleted.
The was fantastic, okay.
The movie was all.
You can flip the sentiment, the movie was horrible. What else could you do? Like random delete, if you were to add a random insert, the movie was not fantastic. That just changes the entire context. So there are again various of these augmentation tools available. Sometimes, in fact, people can also do these random swaps. Might work in certain context, might not work in certain context. Sheep is a likes, not correct English, but it'll still, perhaps it's okay to write. Sorry? Okay, another interesting kind of an augmentation is you start with one language, translate it to another language, in this case German. I unfortunately cannot spell this out. And then you translate it back to English. So then you will get a slightly different version. You could do this many times and you start getting different answers. This one is perhaps the one which you will use a lot. Right? My friend has submitted this answer. I have 4 minutes left. Please give me a slightly different variant of this answer so that I am not caught. Please introduce some small typo so that it looks like I have typed it and I have not got it obtained from ChatGPT. Please also remove the M dashes which give away the copying. So you can paraphrase quite quickly. This literally looks like our students. Model reached 95% accuracy during testing. On the test data, the model secured 95% accurate. Testing showed the model was 95% accurate. And while I'm joking with you as a student, I also remember during my undergrad, there were certain courses. So we had an unsaid rule that the marks were going to be proportional to the length of the answer. So therefore, we exercised a lot of creativity before the ChatGPT-like systems existed. So it was an art. I think it's a lost art now to take a simple thing and to make it non-trivial by writing the same thing in loops. Yes, negation we should not be doing. Not bad to bad will completely change the context. Apple stock to banana stock, you have to understand the entity, whether it's a fruit or it's a company. Bank, you have to understand whether it's the river bank we're talking about, the money bank we're talking about. Sentiment flip, of course, we should not be doing that. Okay, which of these augmentations are preserving the sentiment out of the four mentioned? First and fourth. The second one, restaurant has food, is having no positive or negative emotion. Audio augmentation. Okay, this is very interesting. How can we augment audio? How many of you have been to the audio concerts? How many of you are anyway affiliated with the music club or do or play instruments or sing? Okay, very small subset. How many of you go to the music concerts, have been going to the Spick Mackey events? So what do they typically do at the start of the events? And this is, please don't take it wrongly. So I'm just showing the perfectionism to the tune, right? So they say that the reverb is more, this is less, that, right? So it's very hard for people, outsiders like me, to understand what is going on because it still more or less sounds the same. It takes a very trained ear to figure that out. But this is creating a different kind of a augmented view of that. I don't know to what extent you have looked at audio in your courses. How many of you have done something like signal systems course? How many have not done? Okay, let me ask that. How many of you, so the first years I can understand, second years also have not done that course? Okay, good. So we'll do a quick walkthrough of what we require. So typically there are three different views of an audio sample. The first is time domain. That is what you have been used to looking at. Amplitude versus time. Right? You have seen different waves. In physics you have learned wave functions, etc. right? A sine omega theta plus something, plus phi, right? So that when you plot, you typically see the time domain view. The frequency domain view is to figure out that what frequencies are dominating, and spectrogram will show both of them. So let's walk through an example of this. Let's see if the audio plays.
The quick brown fox jumps over the lazy dog. The quick brown fox jumps over the lazy dog.
This is the amplitude versus time view of this audio recording. We seem to have only 3 seconds, but why do I see so many of these blue, so much of blue in this image? So audio is typically sampled at very high frequency. So when you hear of these terms, 8 kilohertz, 16 kilohertz, 44.1 kilohertz, stereo, mono, that is all depicting the different varieties of audio sampling, as well as whether it's a single or two source audio that you're showing. This is the typical waveform that you're seeing, right? So more amplitude around somewhere in the middle.
The quick brown fox jumps over the lazy dog.
At some parts, maybe this is the quick brown fox jumps over the lazy dog, something like that. In between, there are some pauses. Now, we also have an equivalent of that, which we plot, it's just called as a spectrogram. Again, the x-axis is the same, the y-axis is the peak frequency. So when you speak, there are certain frequencies at which the speech occurs, and there are certain frequencies in between the speech parts, in between the silence parts. Also, you will see certain frequencies dominating. So the quake brown fox jumps over the lazy dog, something like that. So you can see each of these word or phenom being shown over here. And sometimes the high frequencies will also get activated. I don't know whether this is a fox or jumps, one of them. So through this spectrograms also we can figure out what is being spoken. Given an image, given the spectrogram image, you can figure out what is being spoken. Right? So this is higher frequencies, low frequencies. This will become perhaps more clear now. Let's look at some augmentations of that. This is the original one.
The quick brown fox jumps over the lazy dog.
Now let's hear the next one.
The quick brown fox jumps over the lazy dog.
Can you see that the pitch was increased? We'll decrease the pitch. So if we increase the pitch, it will become more woman-like. If we decrease the pitch, it will become more man-like.
The quick brown fox jumps over the lazy dog.
On this case, actually seems more than just changing the pitch. Seems the person is not well. I use a mild word, but I think you understood. Time stretch.
The quick brown fox jumps over the lazy dog.
So this is how our students, I mean not you, students will, given a 5-minute presentation video requirement, they have to somehow fix it. They'll create a 10-minute or a 7-minute one, and then instead of cutting down the script, they'll increase the speed. This is when we don't have high quality instruments.
The quick brown fox jumps over the lazy dog.
Yeah, this is the one which I've personally never understood even in concerts. So it will require a more trained ear to understand that. But you can see that there are some of these changes in the spectrograms as well as in the audio for them. But the underlying audio still remains the same in each of them. We can do other things also. Like we can So in such spectrograms, we can cut some part of the time and we can cut some frequencies. Again, this is similar to the way we have been talking about with respect to images. Although this is not as trivial to remove certain frequencies, because this is not just an image from which you can remove. You have to actually remove it from the audio. How can we remove some frequencies from an audio? How many of you know filters? This is where the signal processing course would have been useful for you to understand this. So certain filters will allow only certain frequencies to work. You cannot allow more than that. And it's taught to cut out higher harmonics. Everyone would know, right? You have studied that for JEE preparation. You want to cut out the harmonics. So therefore you will have some filters which allow only certain frequencies as a max frequency.
Sir, we could cut the audio part also, right?
You would cut the audio part also, as long as you don't cut out almost most of the things or that important thing. And you cannot cut down the audio if you are doing a transcription task. So therefore, depending on the task, speech recognition, it is okay to have some noise, reverb, speed. Speaker, if we change the pitch, the personality will change. So we cannot do that. Music genre, you cannot really change the pitch. That will create a very different kind of a sound. You can of course increase the time a little bit. And with emotion, you don't want to be changing speed. Right? So in fact, the speed at which you speak is a very important indicator of your emotional health in general. So unfortunately, when someone's emotional health might not be good, you might hear that the speech becomes very slurred. You cannot differentiate between two different set of words. Sometimes it can exhibit show some amount of anxiety. Sometimes it's because not proper nervous control is there. So a few guidelines. We do not want to provide augmentations where we ourselves cannot see the label, we cannot predict the label. So some rules of thumb are: do some augmentations, check yourself if you were to label it after that, and how many cases are you correct. This does not mean that you should not be using images at all which you cannot predict, because we have seen previously there are certain images where the human beings would do a very bad job, certain inputs, but the machine is still able to figure out the pattern. So it's not always the case where we want the input to be recognizable, but generally we want that. Now the hyperparameters which we have discussed, one is the probability of applying an augmentation. The second is the magnitude, how strong we want, brightness increased by 1, 2, 4, 5, 20 units, 100 units, and how many transforms do you want to apply. So with these three hyperparameters, we can create something which is known as random augmentation. So therefore, we can have a pool of these augmentations: rotate, flip, brightness, contrast, shear, translate, solarize, posterize, auto contrast. We can choose some random from them. We can then choose the strength of these, and then with certain probabilities pick these up, apply the transform. So we'll end up creating these huge number of transforms through this random augmentation procedures. Any questions till now? Okay, we are towards the end of the lecture. This is a very different and interesting concept, which is known as test time augmentation. Thus far, we have been talking about creating augmentations on the training data set we want to increase. So in this case, at test time, when we want to predict, we will take a test image. This is not training, test image for which we want to predict. We'll apply different kinds of augmentations to that. And then for each of the augmented image, get the prediction. And then finally do the averaging of that or the majority voting of that, depending on whether it's classification or regression. Why do we want to do this? More certainty, we can also get some notion of uncertainty, which is important to understand, under slight modifications. So do you think a prediction is good if it changes by a slight perturbation? Right? So think of this as, do you think a grading scheme is good if your grade depends on 0.1 mark? No. Right? Similarly, if you want a classifier to be good at, you want it to be able to capture the notion of uncertainty and not be very sensitive to slight changes in the input. So therefore, all of these are slight changes, slight perturbations in the input. We'd expect they don't change your output significantly. So this can also give you a notion of uncertainty. Let's say previously you were giving a single number, now you can give plus minus. And secondly, it can also sometimes give you a more robust answer. It could just very well have been that one of your image, the test image was not a very good example, but with certain amounts of augmentation, it ends up being a reasonably good example for your classifier to predict. So take one trivial example. Maybe you are trying to predict a cat in an image, and the cat was very, very small. So overall, if you look at that image, maybe it does not understand. Maybe it just predicts it to be a lion or a fish. But maybe some of these augmentations zoom and pan into the cat. That's one trivial example. This will undoubtedly come with the slower inference because you're required to run this prediction multiple times. Importantly, don't augment the validation data set. So we have, does everyone here know what is a validation data set? Did we study this or no? I am not able to recall. Okay, maybe a subset of you will not know, so I'll skip this for now. Importantly, this is to say that the set on which you're predicting the performance or you're tuning the performance, don't change that. So again, some rules of thumb, they will vary as per your problem statement, your kind of data, your kind of label, the label quality, all of those. So if the data size is very small, you can use a lot of augmentation. For very large data sets, you don't want to be using augmentation. If you have a large data set with, so in some sense, in augmentation, you are adding some notion of noise. If you have very high quality data already prepared, you don't really need to add that and you assume. Secondly, you're adding more compute. So for every, so let's say if you fit with 1 lakh images, you add 2 to 3 augmentations, your computing pipeline will become slower. And in many cases, in such AI systems, the iteration speed is very important. You want to quickly get an answer so that then you can understand, get a feel of the system and then improve it. As opposed to you sit for 1 month and understand that you get 90%. If it's quicker, it's usually better to get 80% in 5 minutes as opposed to getting a 90% after 1 month. Because at 80% you can very quickly iterate and improve. A quick reference, there are different such libraries. Torch Vision for images, Augmentations, which we briefly saw. Many of them we will look in detail in the lab. Torch Audio, Augmentations, and Augly. So all of them you could use for these different augmentation functions. We have these notebooks. I will not run through them today. So I'll just end at this point. There are these different papers which you can read, like we saw this paper, which is cut mix. There is this other paper, let's say spec augment. Augmentations applied to the base input given at the top, from top to bottom. Figures depict the log MEL spectrogram of the base input, no augmentation. Time warping, frequency masking. So we notice the frequency has been masked. Here the time has been masked. So you can see these different transforms. Okay, good. We'll end the lecture here.